Hello everyone. Today we will start about counters. Okay. So a counter is a cascade of flip-flops which is configured to output a given sequence or a specific sequence on application of a clock. So this is the state diagram. So this is having 7 states: S0, S1, S2, S3, S4, S5, S6. Okay, so this is called as state diagram. It is used to describe the operation of a counter. So if suppose you are having 10 states. If suppose it is counting from 0, 0, 0, 0 to 1, 0, 0, 1. That means 1, 0, 0, 1 is what? It is decimal number 9. So 0, 0, 0, 0 means it is 0 state. So decimal 0. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So altogether how many states you are having? You are having 10 states. So it is called as modulus 7 or it is called as mod 7. Whereas in the previous figure they are showing 7 states. They are showing 7 states. It is actually modulus 7 counter. It is not 6, it is modulus 7 because S0, S1, S2, S3, 4, 5, 6. So altogether from 0 to 6, how many states you are having? You are having 7 states. So it is modulus 7. Okay. State diagram of a modulus 7 counter. Each output of the sequence is dependent on the contents of the flip-flop and it is called as a state of the counter. So now coming to binary ripple counter. A ripple counter and difference between the ripple counter and synchronous counter means in synchronous counter all the clock pulses, what you are seeing here, all the clock pulses will be connected to one single clock in synchronous. Whereas in ripple counter the output of one flip-flop will be connected as the input of the clock to the other flip-flop. Okay. So either it will be connected to Q0, either it will be connected to Q bar. So this type of connection of clock is called as ripple counters. Okay. So binary counters output the binary number sequence. A 3-bit binary up counter sequences from 0. If you are having 3 flip-flops, it will count from 0, 0 to 1, 1, 1 and it repeats the sequence on reaching 1, 1, 1. That is, it comes back to 0, 0. Okay. So a cascade of n flip-flops can be used to configure a counter up to a modulus of 2 raised to n. If suppose you are having 3 flip-flops, okay, 2 raised to 3, how many states you'll be having? You'll be having 8 states. That is from 0, 0, 0 to 1, 1, 1. If suppose you are having 4 flip-flops, okay, if you are having 4 flip-flops, it can configure a counter up to a modulus of 2 raised to 4, that is 16 states you will be getting. Okay, so mod 16 you can design. In the same way, in generalized way, it is telling a cascade of n flip-flops can be used to configure a counter up to a modulus of 2 raised to n. So this is a T flip-flop and it is showing an up counter. Let me explain you how it is. See, in an up counter, what you will be having? It is from 0, 0, 0. It will count 0, 0, 1, then 0, 1, 0, 0, 0, 1, 1. That is from 0, it will count till 15. Okay. So this is called as up counter. Down counter, what happens? First 15, 14, 13, 12, 11, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. So this sequence is called as up counter. Okay. So you have to design using T flip-flop a up counter. So you are having T flip-flop. How you have to design? So first thing what I would like to tell is when you are designing for T flip-flop, always you have to see for toggle. That means for each transition, for each clock pulse, it should change from 0 to 1. Okay. 0 to 1, 1 to 0, 0 to 1, 1 to 0. Else you can observe here. See here, Q0, it is changing first 0 to 1, 1 to 0, 0 to 1, 1 to 0, 0 to 1, 1 to 0. Okay, Q1 when it is changing, when Q0 is changing from 0 to 1, it changes from 0 to 1. Okay. Q1 is changing when it is changing from 1 to 0, this will change. In the same way, when Q1 changes to 1 to 0, this will change. Q2 will change. In the same way, when Q2 changes from 1 to 0, this flip-flop will change. That is, this Q3 will change to 0 to 1. I'll repeat. When Q0 is changing from 1 to 0, okay, Q1 will change from 0 to 1. In the same way, when Q1 is changing from 1 to 0, Q2 will change from 0 to 1. Okay. In the same way, when Q2 is changing from 1 to 0, Q3 is changing from 0 to 1. Okay. Or you can also see that Q0 0 to 1 it will change. Q1 Q0 will change alternately 0 1 0 1 0 1. Q1 will change after 2 zeros. It will remain 2 ones, then 2 zeros, 2 ones, 2 zeros, 2 ones. In the same way, Q2 4 zeros, then it will remain with 4 ones, then again 4 zeros, 4 ones. In the same way, Q3 will remain with 8 zeros and 8 ones. Okay, in a simple way. Okay, so now you know T flip-flop. When T is equal to 1, it will toggle. Okay, when T is equal to 1, it will change. Okay, so what we have done in there, what we have done, we have made all the T flip-flops. Okay, all the T flip-flops, it is equal to 1. Okay, so when it has been given the clock pulse. So if clock is equal to 1 and T is equal to 1, it will change 0 to 1, 0 to 1, 0 to 1. So this is fine. Q0 will be equal to 0 to 1. Okay. You can see here. For each clock pulse, okay, for each clock pulse it will change. That is positive edge trigger. When the clock pulse is changing from 0 to 1, okay, this one will be changing from 0 to 1. See this part. Okay, again it will change from 1 to 0. Again at this part 0 to 1. Again at this part it will change. Always toggles 0 to 1, 1 to 0. Only when clock is going or it is at rising edge you can tell, or the positive edge you can tell. Okay, so it will change. So what we have done here, so either you can see, you can keep Q1 is equal to 0 twice, then again once, again twice. For each clock pulse you should see. Okay, so twice 0, twice 1, twice 0, twice 1 you can keep. Okay, and the Q2 4 zeros, 4 ones. Okay, Q3 8 times 0, then 8 times 1. Okay, so now what we can see here is, so this will change when this is 1. So 0 to 1 it will change. Okay, so when this is 1, this is 0, you will not be getting output. Okay, again for next clock pulse, when this is 0 and this is 1, so clock pulse have come 1, so again it will change. So for 2 clock pulses it will change. Okay, in the same way for 4 clock pulses this will change. In the same way for 8 clock pulses this will change. The same thing what we have explained in a simpler manner. So now you can see 0 0 0. Okay, next what it is, 0 0 0 1. Next 0 0 1 0. 0 0 1 1. 0 1 0 0. That is, this is 0, this is 1, this is 2, 3, 0 1 0 0 4, 0 1 0 1 5, 0 1 1 0 6, 0 1 1 1 7, then 8, then 9. Okay, you can see 1 0 0 1 9, 1 0 1 0 10, 1 0 1 1 11, 1 1 0 0 12, 13, 14, 15, then back to 0, 0, 0. Okay. So you all know T flip-flop when it will toggle, when it is equal to 1. So it is given to count enable, which is equal to 1. In the same way for the other flip-flop also you have to do. For other flip-flop, when we see JK flip-flop, when it will be equal to 1, it will toggle. Okay. And whenever they are telling negative edge triggered, what you have to do is you have to put a bubble over here. Okay. Negative edge triggered, always put a bubble. Okay. So when it is 0, then it will be active. Okay. So you have to put a bubble. So design a 4-bit binary ripple up counter using negative edge triggered JK flip-flop. So JK flip-flop, when it will toggle, you can see the truth table, what I have given before. So when it will toggle, that means when it will move from 0 to 1, 1 to 0, when JK is equal to 1, it will toggle. Okay. So now JK is equal to 1. So it is negative edge triggered. Negative edge triggered in the sense, it is, what do you mean by negative edge triggered? When it is going from 1 to 0 or at falling edge, we tell it as negative edge triggered. Okay. So when it will be active, when the flip-flop will be active, when it is going from, when the clock pulse is going from 1 to 0, it will be active. Okay. So at that time it will toggle 0 to 1, 0 to 1, 0 to 1. Again, what we have done there, the previous clock, here clock what it is output from this one. Here clock what it is, this is ripple counters. Ripple counters are such that the clock pulse is given to the previous output. Okay, clock pulses are given to the previous output. When it is synchronous counter, all the clock pulses are given at the same time. Okay, are given at the same time. So Q0, you have seen, this is Q0. So this depends on the main clock pulse when it is going from 1 to 0. Here Q1, what again we have done, it is negative edge triggered. So when this one is going to 1 to 0, this will act as a clock for the second flip-flop. When it is going from 1 to 0, it will change. Okay, it will change from 0 to 1. Again this one, when it is going from 1 to 0, it will change. Okay, in the same way, again Q2, again the same thing, output is given to this one, Q1. So when it is changing from, and it is negative edge triggered, when it is changing from 1 to 0, this will change. When it is changing from 1 to 0, this will change. When it is changing from 1 to 0, this will change. Again Q3, what we have done, the clock pulse is given to the previous flip-flop. So when it is changing from 1 to 0, this will change 0 to 1. Okay. So when it is changing from 1 to 0, this will change. Okay. So now Q3, 0, 0, 0, 0, 0. Then 0, 0, 0, 1, 1. This is 2. This is 3. Okay. This is 4. This is 5. 6. 0, 1, 1, 0 is 6. 0, 1, 1 is 7. 1, 0, 0 is 8. 1, 0, 0, 1 is 9. 10. 11. 12. 13. 14. 15, 1, 1, 1, 1 is 15. Again back to 0 and it will repeat. Okay. So these are up counters. In the same way you have to design for down counter also. So now design a 4-bit binary ripple up counter using positive edge triggered D flip-flop without a count enable. So now we know JK flip-flop, it will toggle when J is equal to K is equal to 1. We know that T flip-flop will toggle when T is equal to 1. Compulsion is that clock should be given. Clock should be given as 1. So now we don't know, in D flip-flop it will not toggle. Okay, whatever data is given, the same data will be appearing at the output. When D is equal to 0, when D is equal to 0, this will be 0. When D is equal to 1, this will be 1. So you have to think in such a way that it should toggle. For the next clock pulse, if 0 is being given, 0 will come. So for next clock pulse, again 1 should be given. Again for next clock pulse, 0 should be given. So what can we do? We will be doing in such a way that we will connect to Q bar. Okay. When it is 0. Okay. So 0 will come here. So this becomes 1. So 1 will come again here. So when 1 comes here, this becomes 1 and this becomes 0. Again for next clock pulse, what happens? This 0 comes over here. Okay. If this is 0, again this will be 0 and this will be 1. So when this is 1, again it comes 1. So we are seeing in such a way that it should toggle for each clock pulse. If the first flip-flop comes, then the second one will be the same. Okay. So now, and this is positive edge triggered D flip-flop. So positive edge triggered D flip-flop it is. See here. So now what we will do? Clock is connected here. Okay. Remember one thing, if it is up counter, okay, if it is up counter and if it is, I'll give you the table if you want. If it is up counter and if it is positive edge triggered, you should know where the clock pulse to be connected. Okay, if it is up counter and if it is positive edge triggered, clock pulse will be connected to Q bar. Okay, got? And if it is negative edge triggered flip flop and if it is up counter, clock will be connected to Q as you have seen in JK flip flop using negative edge triggered. Got understood? So in up counter, if it is positive edge triggered, clock will be connected to Q bar. If it is negative edge, it will be connected to Q. Okay. So if it is down counter, opposite of that. If it is down counter and if it is positive edge triggered, it will be connected, clock will be connected to Q. And if it is negative edge and it is a down counter, it will be connected to Q bar. I'll give you the table. Okay. So now it has been connected. Let us see the waveforms now. See here. For each clock pulse, what it is when it is changing from 0 to 1, when it is changing from 0 to 1, this is, it will toggle for each clock pulse. Okay. It will toggle for each clock pulse like this. When it is going from 0 to 1, it will toggle. 0 to 1, it will change. Again for the next rising edge, again it will change from 1 to 0. Okay. So what we have done, we have given clock pulse. So here what happens? We have given to Q bar. Okay. We have given to Q bar means it is like negative edge triggered. So negative edge triggered means when it is moving from 1 to 0, it will change. Next one. So Q1 will change when it is going from 1 to 0. When it is going from 1 to 0, it will change. So it remains 0, 0. This Q0 will act as clock pulse for the next flip flop. So it is, we have connected to Q bar. So Q bar means when it is changing from 1 to 0, this will change. When it is changing from 1 to 0, it will change. 1 to 0, it will change. In the same way, Q2 what we have done, we have given to Q1 bar. Okay, Q1 bar means when it is changing from 1 to 0, it will change. When it is changing from 1 to 0, it will change. Q3 what we have given, where we have given the clock pulse, we have given to Q2 bar. Q2 bar means when it is changing from 1 to 0, this will change. So you can see if you want, this is 0, 0, 0, 0. This is 0, 0, 1. Again it will be 0, 0, 1, 0. Again this one will be 0, 0, 1, 1. Like this you will be getting for D flip flop. Till 1, 1, 1 you will get, again it will reset to 0, 0, 0. Okay. So now coming to counter with parallel load facility. So this is till now what we have seen is it will be counting from 0, 0, 0 till 1, 1, 1, 1. Now we can also design our own counter to count from 0, 0, 0, 0 to 1, 0, 0, 0. Okay, that is 0 to 8. So 0 to 8 means how many mod it is, how many states will be having 0 to 8? We will be having 9 states. So 9 states means you will be having mod, it is called as mod 9 counter. Okay, so now, so you are designing in such a way that it will count from 0 to 9. Oh, sorry, 0 to 8. So it is mod 9 counter. If you are designing for 0 to 9, it is called as mod 10. If you are designing from 0 to 7, it is called as mod 8. Okay. So now, so this one, D0, D1, D2, D3, whatever you will place here. Okay, inputs. You can place the inputs over here. and 1 at the count input. And 1 at the count input, what happens? Would enable the up counting. When I put 1 here, it starts up counter. Okay, it starts up counting. So from 0, 0, 0, 0, it will count till 1, 1, 1, 1. Okay. So when it reaches 1, 1, 1, 1, okay, and it reaches 1, 1, 1, 1 after reaching 1, 1, this carry output will become 1 when it goes to 0, 0, 0, 0. That means again it starts its counter. 0 to 1, 2, 3, 4, 5. When at the last when it reaches 1, 1, 1, 1. Okay. So when it reaches 1, 1, 1, again from 1, 1, 1 back to 0 it should come. So 0, 0, 0, 0. So what happens here? Carry output will be equal to 1. So this goes high when the transition from 1, 1, 1, 1 to 0, 0, 0, 0 occurs. So this is load, this is count, okay. This is the clock pulse and this is the carry output. Let us see one problem, it will be clear for you all. So configure a synchronous 4-bit counter with parallel load inputs to count from 0, 0, 0 to 1, 0, 0, 1. So you are designing your counter such that it should count only from 0 to 9. Okay, after 9 it should come back to again 0 only. So now let us see. So it should reach 9. Okay, so for that what I'll do, I will load 0, 0, 0 here. 0, 0, 0, 0. Okay, and I'll start counting. Okay, this becomes 1. I've given 1 and I've given the clock pulses also. When I've given the count 1, what it will do, it will start counting. So it will count 0, 0, 0, 0, 0, 1, 0, 0, 1, 0. Okay. Sorry, 0, 0, 0. So 0, 0, 1, 0, 0, 1, 0, 0, 0, 1, 1. So I should design in such a way that, so when it reaches 9, it should reset back to 0, 0, 0, 0. Okay. So when it reaches 1, 0, 0, 1, it should reset back to 0, 0. So for that purpose, what I will be doing is, I will see that when it reaches 9, load will get 1. When this becomes 1, what happens again? It will load this content. That is whatever you have placed here, that will get loaded here. Okay, as usual, the count is 1, it will again start counting. So for when it reaches 9, that is when it reaches 1, 0, 0, 1. So I'll use an AND gate. Okay, when I'll use an AND gate, so I'll connect it to Q0 and I'll connect it to Q3. So 1 into 1, you'll get 1 over here. So that 1 will reach here. So when this load is equal to 1, what happens? Whatever is there at the input side, that will get loaded. So this becomes again 0, 0, 0, 0. So again the count enable, it will make count which is equal to 1. Again it starts up counting. So let us see whether for the other counts this becomes 1 or no. In such a way you have to design that only for 9 you should give 1 over here. For other counts you shouldn't give. So for other counts it will be 0 only. So when it is 0, that will not get loaded. Okay, understood? If you want, you can check. If it is, this one is 0, that is I'll see for Q3 and Q0. It is 0 and it is 0. So when I use an AND gate, it will be 0. This is 0 and this is 1, again it will be 0. 0, 0, again it will be 0. Only for this number, okay, 1, 0, 0, 1, that is Q3 and Q0. If it is equal to 1, I'll be getting 1 as the output of the AND gate, and that 1 will be loaded here. When it is loaded here, whatever the inputs are at the input side, that will get load and it will start counting. Okay, anything it may be. You can design for 0 to 7, any gate also you can use, but you have to design in such a way that load will be given 1 only when your count is being reached, so that whatever you will place here, that will come here. If suppose you want to design for 2 to 7 also, you can design 2 to 8 also you can design. When you design in such a way that when you start your counter from 2, it should be kept here 2 only. That is 0, 0, 1, 0. So that 0, 0, 1, 0, 0, 1, 0 will come here. Okay. So 2 comes here, it will start counting again. You should design in such a way that you can use any sort of gate so that when it reaches your count, this load will be 1. Again, whatever you have placed here, if suppose you have placed 2 here, that 2 will come here and it will start this count. Okay, in such a way you have to design. Configure a 8-bit synchronous counter using two 4-bit synchronous counters. So now you have to design in such a way that it will count 8-bit. So here it is, we are having, this is 4-bit counter. Why? Because we are counting Q3, Q2, Q1, Q0. So it is 4-bit. So what they are telling, we have to configure a 8-bit synchronous counter. So this is Q4, Q5, Q6, Q7. This 4 bits and this 4 bits, it becomes 8-bit. So as usual, you will be having count, you will be having load. Okay. You will be having count, you will be having load. So now I'll start the count. Count is given 1. Okay. So it will start 0, 0, 0. Okay. So this will start its count. It will reaches to 1, 1, 1, 1. Okay. When it reaches to 1, 1, 1, what happens? It will again move to 0, 0, 0, 0. So when it moves to 0, 0, 0, there is a carry because we have seen previously when the transition from 1, 1, 1, 1 to 0, 0, 0, 0 occurs, this carry will be generated. So when this carry has been generated, what happens? Will be given to count. It will start its count. Okay, again it starts counting. So this is 8-bit synchronous counter using two 4-bit synchronous counters. See here, I've told you, you can design your own counter. So here it is, design a mod 5 synchronous counter to sequence the first 5 states from 0, 0, 0 to 0, 1, 0, 0 and repeat. So okay, using a 4-bit synchronous counter with parallel load facility. So now, so this is, I've kept 0, 0, 0, 0. It should count from 0, 0, 0 to 0, 1, 0, 0. So altogether, how many states you'll be having? You'll be having 5 states. That is 0, 1, 2, 3, 4. Okay, this is 0, 1, 0, 0 is 4. From 0 to 4, you'll be having altogether 5 states. So it is called as mod 5 counter. Okay, so now what, so it will count 0, 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 0, 1, 1, then 0, 1, 0, 0. So previously, what I'll do, I can connect directly this Q2 to load. So when it reaches 4, okay, so when it reaches 4, what happens? This one comes at the load. So when it comes load, what happens? Whatever is at the input side, that will get loaded and it will start its count again. Again, when it reaches 4, what happens? Q2 is 1, so it is given to load. Again, when this becomes 1, what happens? Again, whatever is at the parallel inputs, whatever is at the input side, that will get loaded and again it will start its count. In the same way, it repeats. In the same way, you can design anyhow 2 to 8, 2 to 5, any counter you can design of your own by using any sort of gate, but you should see that it will count the given sequence itself. So here they have told repeat the same example to sequence the last 5 states to 1, 1, 1 and repeat from 1, 0, 1, 1. So what I will do, 1, 0, 1, 1 is being given here because it should start from 1, 0, 1, 1 only. It cannot start from other. It cannot start from 0, 0 because they have told it should come from 1, 0, 1, 1 only. So 1, 0, 1, 1, when the count starts, it will get loaded here and it will start its count. Okay. So when it reaches 1, 1, 1, 1, what happens? A carry will be generated. This carry, what happens? Is given to load. Again, when it becomes load will be equal to 1, what happens? Again, this one will get loaded. Okay. When this one will get loaded, again it will start its counts. Okay. When again it reaches 1, 1, 1, 1, again it will it is been given to load. Again it will load 1, 0, 1, 1. Again it will start its count. So it will count from 1, 0, 1, 1 till 1, 1, 1, 1. So now this is called as ring counter. Okay, this is important. Ring counter, Johnson counter will be having. Okay, these are very important. So ring counter, the name itself indicates it will get ring. Ring in the sense it will get the last bit. It will get moved like circular it is. So suppose you are having 1000. So this 0 should be moved again to Q0. Okay. Again this 0 should be moved to Q0. Again this 0 should be moved to 0. Moved to Q0. So what happens? Q0 here if it is 1, here it will be 1 for the next clock pulse. Here if it is 1 for the next clock pulse, here it will be 1. So here here it is 1, it will be for the next clock pulse, here it will be 1. So this what we will do from the last bit, again I'll be giving it to the uh, first bit. So that is we are using D flip-flop. Why we are using D flip-flop? Whatever is the data that will be given to the output. Whatever is the data that will be given to the output. If suppose D is equal to 1, okay. So here it is 1, here it will be 0, here it will be 0, here it will be 0. For the next clock pulse, this 0 will move here. Okay, so here it was 1 previously. So this 1 will move here. Okay, so what it becomes? 0, 1, 0, 0. For the next clock pulse, what happens? This 0 comes over here. So what happens here? 0, 0, 1, 0. For the next clock pulse, what happens? It will become 0, 0, 0, 1. Okay. So this is mod for ring counter. So you have to remember this and you have to remember this circuit. How you'll be doing mod for ring counter, and you have to give the sequence. Next, coming to Johnson counter. It is called as Johnson counter, it is called as switch tail counter, or it is also called as twisted ring counter. So in twisted ring counter, what we'll be doing, we'll be giving output, the last bit output to the Q bar. Okay. So what happens when we'll be giving to Q bar? So this is 0, 0, 0, 0. So we have given to Q bar. So this is 0 means this one will be 1 and will be getting shifted. So again this one is 0. So again Q bar we have given. So this one becomes 1. So again this is 0. Again 1 will come here. So again this is 1. What happens? Here it will be 0. Okay. Again here it is 1. Here it will be 0. Again here it is 1. Here it will be 0. Again here it is 1. Again here it will be 0. So this again repeats the same thing. Okay. You can check here. Suppose at the starting this is 0, 0, 0, 0. Okay. For the next clock pulse, what happens here? If this is 0, this becomes 1, right? So what happens here? 1 will come here. Okay. So 1 when it comes here, so this becomes 1, 0, 0, 0. So this is 0, this is 1. Okay. Again 1 comes here. Previously what it was? Here it was 1. So this 1 will shift here. Okay. This 1 will come here. So this is 1, 1, 0, 0. Again this is 0 means this one will be 1. Again this 1 comes here. So what happens here? Whatever it is, it will get shifted. So this one is 1, 1, 1, 0. Again this is 0. So what will be here? It is 1. So again 1 comes here. Okay. So 1, 1, 1, 1. So what happens? This is 0. So this, as this will be 1, this will be 0. So this 0 comes here. Okay. When this comes here 0, so this becomes 0. So this is 0, 1, 1, 1. Again 0, 0, 1, 1. Again 0, 0, 1. Again back to 0, 0. So altogether how many states you'll be having? You'll be having 8 states. 1, 2, 3, 4, 5, 6, 7, 8. So if it is 8 states, it is called as mod 8 Johnson counter. Sequence of mod 8 Johnson counter. So again Johnson counter we are having with odd number of states, where this state, that is 1 1 1 1, is been removed by using an AND gate. So this is, we have connected to NOT, that is Q bar. Which one has been connected? Q2 and Q3 is connected to bar and it is been given to Q naught. Okay, same thing, Q2 and Q3. Here it is 0 0. Okay, Q2 Q3 is 0 0. Then Q2 bar Q3 bar will be 1 1. So 1 1 will be given to 1 here. Okay, in this way Q2 Q3 is 0 0. So what will be Q2 bar and Q3 bar? It will be 1 1. So output of AND gate, when it is given as 1 1, it will be 1. So that one will come here. This one will get shift here. Okay. So again it is 0 0. 0 0 means what will be getting? You will be getting 1. Okay. So this one will be given here. So again here what happens? Either of one will be 0. That is, it is connected to bar. Okay. So you will be getting 0. Okay. So again both will be 0. So you will be getting 0. So both will be 0. Again you will be getting 0. This AND gate. Q2 and Q3 is connected. Q2 and Q3 bar is been connected to the AND gate and that is given to Q naught. And for each clock pulse it will get shifted. Okay, so it is mod 7 twisted ring counter. So configure 4-bit ring counter using a universal shift register it is. So the connections are as shown below. Keeping A0 at logic 1. Okay, A0 at logic 1 and A1 is equal to 1. A1, if it is 1, it will act as parallel load. So it will load the inputs. Whatever parallel inputs you are giving, it will get loaded. So if it is 0, it will start counting. Okay, this is serial shift left. This is shift right. So what they are given? If A1 and A0 is 0 0, it should hold. If it is 0 1, okay. If this is A1, if this is 0 and this is 1, it should shift right. Okay. If it is 1 0, if it is 1 and this is 0, it should shift left. And if it is 1 and 1, it should load. Okay. So if this is 1 and load, if it is 1, what happens? It should load whatever the inputs are there. So inputs what we have given 1 0 0 0. So the 8 will be been loaded over here. Okay. When this is 0, when this is 0 and this is 1, what happens? It should shift right. So that will be given to the shift right. When 1 comes here, it means it should shift right. So when it is 1 1, it should load. When it is 0, the output should be as it is. In the same way, one more example is been given. Repeat the example to implement a 4-bit twisted ring counter. So twisted ring counter means we'll be connecting it to the bar. Okay, the last Q3 bar will be connecting. So Q3 bar we want means we'll be connecting it to a NOT gate. Rest all will remain the same thing.